Hello dear students, welcome everyone. This is Amish Sheikh, Faculty of Chemistry. So welcome you all once again. Now today we'll see the how to elucidate the structures particularly with the help of what X-ray diffraction methods now. Okay, so stay connected with us. Definitely you will enjoy this lecture because this is a very interesting point of regarding that structural identification now. How this X-ray or X-ray diffraction is useful to get the structures of what any unknown crystals now. Okay, and you know that X-rays are nothing but the highly energetic radiations. When we are directly that radiation strike on that any solid system, so there what will be happen now, the reaction will be takes place between your in X-ray radiation as well as in the your crystals. Okay, so stay connected with us. Now as you can see that here, so one atomic model is given to you. There are some protons and neutrons are present in that center. Along with that there are the electronic shell is there. So this is the first shell of the electron and this is the second shell of the electron. So when you can see that particularly whenever we have highly energetic radiations are directly strike to the system or strike to that atom particle, what will happen now? So there is a electron will be ejected now. Either the electrons are ejected from the valence or from the core now. So these electrons are called the valence electrons because they are present at the or they are away from that nucleus. That's called the valence. And while those are nearer toward the nucleus, that will be called as a core electron, right? So you know that core electrons are tightly bonded to the nucleus while valence electrons are loosely bonded, right? So that means the least energy will be required to remove that electron, particularly from valence one. And you know that every shell having some specific binding energy. You know that these two electrons have same binding energy, but these electrons are different because of they are present in the next shell now. And you know that next shell means less attraction will be there particularly. So in case of what solid state now, that is actual property that will be very useful to elucidate the structure of any crystalline material. And that's why X-ray spectroscopy or what X-ray diffraction method is very useful to elucidate the structures like sodium chloride, like potassium chloride, cesium chloride, etc, etc. Okay, so now first of all, what is actually the principle now? Okay, now you can see here particularly here, now this is the atomic model is given to you particularly, and in that case, so actual instrument is this one now. So this is the instrument, and you know that solids are what very perfectly they are one can call orderly arranged. And you know that when these incident radiations are strike to that sample now, they get interacted with your atoms, okay, or the particularly the solid system on the surface, and they will be get reflected now. They will be get what reflected particularly, and that method is called what the diffraction method. Okay, so you can see here, so this method is called as the X-ray diffraction method, where the rays are strike to the system or your atom, solid atom particularly, and then it will be get diffracted particularly one can call, okay, with particularly angle now. So here the incident angle and the diffracted angles are what different particularly. Okay, so what is the equation for this one? So Bragg studied this system or the studied material science particularly, that is solid state material, and according to the Bragg's equation here, n lambda is equal to 2d sin theta. This is called as the Bragg's equation. So here nothing but the what lambda is a wavelength, you know that, which is measured in nanometer, okay, of an X-ray. N is an integer number, and d is nothing but the distance. D is nothing but the what, your distance between these two or lines particularly, or any crystal planes particularly. Okay, here theta is the angle of what incident. So based on that four parameter like wavelength, n, then d and theta, you can easily predict what the n lambda, right? So we have, so I will show you the animation for that particularly. You can observe here, so how that X-rays are strike to the systems and how it will be diffracted now. And here the Bragg's law is applicable to here now. So incident light and what diffracted light, diffracted rays particularly here, and the Bragg's law is nothing but the what, n lambda is equal to 2d sin theta, while the d is nothing but the your spacing distance, right? So you can again observe here. So these are nothing but the incoming or incident radiations, that is X-ray, and they when interacted with your solid sample and they get what diffracted now. So diffracted radiations make the diffracted light makes the what some pattern that will be called as a diffraction pattern now. Okay, so based on that we can identify the type of what crystals. So those who are unable to get the actually what is that X-ray diffraction method now, so you can observe from this animation particularly here. So X-ray, this is what the X-ray from which the source particularly, and they will be interacted with the what specific angle. Okay, and then when strike to the system now particularly they travel and then goes to a detector now. So here the change in the angle now particularly from incident toward the diffracted one, so that will be the most important phenomena. Okay, so which is for elucidation of what the solid materials. Okay, this is called as the X-ray diffraction phenomena from which one can get the diffracted pattern now. So here you will get the diffracted pattern, and you know that for each and every crystal the diffraction pattern is unique, and that's why based on that we can identify the your type of a crystal. Okay, we'll see that based on that n lambda is equal to 2d sin theta, we have one some numerical based on that. Okay, so the planes of crystals are 0.281 nanometer apart, and the angle is equal to 11.8. Okay, then for the first order diffraction, what okay, so particularly the terms are given to you. So plane of the crystals are what 0.281 nanometer, angles are 11.8, and for the first order diffraction what will be the wavelength for that X-ray now? We have to find out the wavelength, which what wavelength is which wavelength is used particularly here. So here 2q is equal to, or 2 theta is equal to 11.8, where q is equal to what 5.9. So and n is equal to 1 for first order diffraction, and wavelength is given in 2.81 nanometer, so it will be converted into the, this is sin theta, this is 5.9 particularly for n lambda is equal to sin theta, equation is there. So here 0.058 nanometer is the answer. Okay, sorry, picometer. So you can see here with the help of what your equation, that is n lambda is equal to 2d sin theta, right? So here n is equal to 1, right? So n is equal to what, because it is the first order system, so n is equal to 1, so that's why 1 into lambda, we have to find out the lambda. So 2 into d, what is the d now? D is a again distance between that planes particularly here, 2 into, and which will be what 0.281, this will be the how much it is 0.281, and sin theta, you know that sin theta, so already we have a theta is equal to 5.9, and sin 5.9 is equal to how much, then 2 into 0.281 into sin 5.9, sin 5.9. So if you solve this one, so you will get your answer is 0.058 in picometer, like this. So this is what the actual wavelength of what X-ray now. Okay, you can also convert into the what nanometer to 1. Okay, this is what the X-ray diffraction, how it will be helpful to get the structures. So let's see the some example of ionic crystals. You know that for the first example of ionic crystal is what rock salt, that is also called as what the sodium chloride. This is the actual structure or animation of what the sodium chloride now, and you know that sodium chloride is an example of face center type, face centered cubic, where coordination number is 66, means what, where each single chlorine atom, that is Na plus, is surrounded by 6 Cl negative ion, or while each Cl negative ion is surrounded by 6 Na plus ion. Okay, fine. The calculation of number of atoms are particularly here, so the answer will, for FCC your answer will be, so for that FCC your answer will be what 6. Okay, 6 is to 6, and now we can find out the number of atoms now. So all the chlorines are at corners. You know that at corners contribution will be 8 into 1 by 8 is equal to 1, and chlorine at the present at what some faces now. Also the chlorine at the faces means 6 into 1 by 2 is equal to 2. That means there are total 4 chlorine atoms are there. Okay, and sodium at the edges, now there are 12 edges are there, and each contribution will be 1 by 4 is equal to what the 3 now. Okay, like this one. So sodium at the body center now, so there are total sodiums are what 1 at the center and 3 at the faces now, edges, sorry. So from that if you combine together, so the chlorine and what sodium are 4, that is unit cell consists of what 4 now, that's why it is an FCC type. So here 4 Na and 4 Cl will be present at the unit cell now. This is actual what picture of what sodium chloride, and this structure is obtained due to the because of what X-ray diffraction method. Now the structure of what KCl, now how KCl is differed. KCl is again face centered system now particularly, and here the molar mass of what KCl is 74.55 gram per mole. Density particularly in the solid state is 1.9 gram per cubic centimeter, and you know that the melting point of what potassium chloride is 1040 Kelvin and 1690 Kelvin respectively. Melting and boiling points is given. Okay, and potassium chloride is completely ionized, that is K plus and Cl minus when you put in the water, and this is what the structure of what the potassium chloride particularly. Okay, so thank you for watching this lecture. So hope all of you are enjoy this lecture. Stay connected and stay safe. Thank you.